Yes, good morning everyone. Welcome back.
Morning, sir.
Yes,
Good
hope it is
morning.
audible. Is Shaktivel?
Yes, sir, audible.
Okay. So, any doubts from yesterday's class? So, let me begin the session with a quick revision of what we have covered yesterday.
Okay.
Yes, any doubts, Shaktivel?
No, sir.
Okay, okay. So, yesterday we played with only first order system, given three time domain inputs, k by tau s plus 1, got excited by the input command r of t, the output response c of t, the control variable c of t, the reference input labeled as r of t. So when r of t is equal to del of t, we got c of t is equal to, yes, let me have a simple table. Input is r of t, the output is c of t. When input is del of t, yes, what was the response? Standard first order. Yes, del of t is input. What is the output? K by tau e power minus t by tau into u. Where is the pole of the system? Where is the pole of the system? Is the system is stable or assuming tau is greater than 0? Tau is a positive parameter. Tau is a positive parameter. Real parameter, positive parameter, greater than 0. And then tau s plus 1 equal to 0 is the location of the pole. Then tau s equal to minus 1, s equal to minus 1 by tau. The pole is on the left hand side. Comment on stability of the system. As per the Bibo stability, yesterday we concluded a system is Bibo stable only when all its poles are falling on left hand side of your S plane. This is your S plane. So this is your j omega axis, imaginary axis minus j omega, and this is your positive real, and this is your negative real. Okay, yes. So we are expecting the system to have the poles on left hand side as per the Bibo stability. Then the system is said to be stable. Therefore, the given system is a stable first order. Okay, we are talking about response of a stable first order, how it is reacting to a unit impulse input. Okay, this is what we call as unit impulse input. The corresponding response known as unit impulse response. Okay, unit impulse input. Then we have given a step input. Then we excited the same system by a ramp input. Step input a into u of t, ramp input at into u of t. Yes, the response for a step input, the system reacted like ak into 1 minus e power minus t by tau into u of t. Then it's easy to remember for a ramp input. Remember ramp input, yes, it is going to be same as your, yes, in terms of k is there. So bring that k also into the picture. So it is going to be ak t into u of t, same as your ramp magnified by k, minus it is ak into tau 1 minus e power minus t by tau into u of t. Remember everyone? Correct?
Yes, sir.
Okay, yes, that's these are the important conclusions we made. So whenever a problem is made on first order system, okay, the problem may be belong to the transient part or may belong to the steady state part. Okay, so this is how you can exploit the equations to answer the given problem. Okay, So this equation C of t is consisting of both the steady state part as well as transient part. Okay, so depending on, and all these responses will reach steady state at what time? All these responses will reach steady state at what time? Settling time of any input command, the system is going to settle, the first order system is going to settle at what time? 5 times tau approximately. Getting? That's your settling time. That's where it is going to settle at its steady state value. Clear, everyone? Easy?
Yes, sir. Yes.
So these are the important conclusions. A quick summary of what we discussed yesterday. Already I have given another name for time domain response analysis. It is also known as transient performance stability analysis. Transient performance stability analysis. Transient performance come stability analysis. That's a better way to define this response. Okay, right? So you're talking about stability even during transient response. That means stability means here Bibo stability only, whether the output is still bounded during transient period or not. Okay, the output is bounded, okay, as per the graphical representations we had, except your ramp input, because ramp input we should not apply final value theorem. But anyway, as per our observation, your output response is always lagging behind your input by some factor. This is a factor. The output response is lagging behind your input by some factor, assuming k is 1. Okay, k less than 1, the response will be further less than 1. K greater than 1, the output response may be greater than your input response, but still it is a bounded one. If time is bounded, this is bounded input, this is also bounded output, even for a ramp input. So time bounded input command we can say. Okay, so another important point I want to say, systems, control systems are broadly classified into, one is called regulatory control, another one is known as servo control. Okay, broadly classified into regulatory or servo control. Okay, so here in regulatory control system, the input command remains constant. Input command remains constant. That means you are changing. A step change is a good example of regulatory. Say, for example, I'm controlling my air conditioner. Initially, my room temperature is around, for example, initially my room temperature is around 30 degrees C, or as of now, maybe you can take around 35 degrees C, but I'm asking the temperature as 25 degrees C by turning on my air conditioner. It's a negative step change. The present temperature is 35, but you are asking plus 25. So the command change is given at time t equal to 0 second. Okay. And after that, you are not going to change your command throughout the day or throughout the class. Okay. Assuming you are in the classroom and I'm turning on my air conditioner, all the air conditioners giving a 25 degrees C. So at time t equal to 0 second, this has happened. After that, I'm not going to take the remote once again till the class is over, till the break is arrived. Okay. Or given. Okay. Yes, that's a good command. Okay, that's what we call as a regulatory command, regulatory control command. Such a system is known as regulatory control system, where the input command doesn't change often. It remains constant. Okay, throughout the control system is an on condition. Are you getting my point, everyone? Yes. Yes or no?
Yes, sir.
And servo control is the one where the input command is going to change. That means your R of t is going to be really a function of time. A good example is your ramp input itself. It is AT into U of t, where you are expecting the system to follow the input command. That means it has to raise like a ramp. So that's why you are giving such a command. Okay, so that's a command usually given for a missile or rocket. Okay, missile or rocket. Just see the trajectory of missile or rocket. So it is its altitude. At least you take its altitude. The altitude of the rocket is keep on changing. Okay, with respect to what time? Or you can take the position of the rocket, 3D position. It is going to have X, it is going to have Y, it is going to have Z. Okay, X position, Y position, Z position, all are going to vary with respect to time. Okay, so you are controlling the position of the rocket in the space. That is going to be a three-dimensional space that is having X dimension, Y dimension, and Z dimension. All these parameters are changing with respect to time. So such a control, we call it as servo control. When the input command changes with respect to time, the command is servo command, and the corresponding control system is known as servo control system. Are you understanding this point? Simple point. If the input command remains constant, Okay, so after a finite change like a step input, then what the system is going to do, or once you turn on the air conditioner and feed 25 degrees C, air conditioner is simply going to regulate your room temperature to 25 degrees C. That's what it means. Why the name regulatory? The job is simply it has to regulate the room temperature. That's all. Okay, or you may use a control system, for example, stabilizer. Stabilizer is also a control. What it is going to control? It is simply going to regulate the voltage to be a constant, irrespective of the load conditions. It has to maintain the voltage like a constant voltage stabilizer we call. That is also a regulatory control example. Okay, where you are fixing the voltage to be like a constant. So it has to regulate that. Yes, it's a regulatory control. Okay. So when the input command is remaining constant, we call it as a regulatory control system for a control system. For a control system, if the input command keep on changing with respect to time, such a control system, we call it as servo control system. That means what we are checking here is by giving a step input, whether my control system k by towers plus 1 can act as a regulatory control system or not. Yes, that's answer when k equal to 1. When k is equal to 1, for example, you are giving a command of a and the response is also raising to a. Yes, at least after some time it is going to follow. Yes, it's a good regulatory control. So then I'm asking a second question. So a system of k by towers plus 1 is a good one for regulatory command. Can it be good one for a servo command? So that's why I'm giving a ramp input. Then there is a lag. The output response, if k is equal to 1, if k is equal to 1, it is going to be 80 into u of t. The input is also 80 into u of t. Even though you make the closed loop control system with the k is equal to 1, but it is going to suffer because of this deviation. So that means output response may not be equal to your input command. Then you are concluding that k by towers plus 1 system excited by a ramp input or a servo command may not exactly follow your input command, okay, as expected, or as happens in step input command or regulatory command. It is good for regulatory but not good for servo control because it is going to have a lag with respect to the input command, assuming k is equal to 1. Hope everyone is catching this point, getting this point. Yes,
Yes, sir.
getting Bonesh, getting Monisha.
Yes, sir.
Okay, Swarna following, right?
Yes, sir, following, sir.
Okay, yes. So that's how control system will be further classified. Both are closed loop control systems. One, the input remained constant, known as regulatory control. Input changing with respect to time, known as servo control. That's all. Okay. So with this conclusion, let us approach the time domain response of a second order system. What second order? What second order? Yesterday I have given an underline. It's a underdamped second order. Second order underdamped system or underdamped second order system also we can say. Second order underdamped system or underdamped second order system. By default, its model is given by k into omega n square in the numerator. Denominator is a square plus 2 zeta omega ns plus omega n square. Examples already given, mechanical as well as electrical examples given. Say mass spring damper MKB system, mechanical translational system will resemble second order, or a simple RLC circuit also will resemble RLC series circuit, okay, or parallel circuit also, okay, but what I have given is only RLC series circuit. RLC series circuit also resembles the second order, okay. If it is MKB system, input is force, output is the displacement of the mass. If you remember, if it is RLC circuit, input is a voltage V in of t and output is V naught of t. Okay, accordingly, depending on the system, you get your omega n, you get your k, you get your damping. Okay, influenced by your system parameters. If it is mbk, omega n and zeta influenced by m, k, and b. If it is RLC, omega n and damping and k influenced by this RLC parameters. Okay, just a revision of what we have done in the unit number 1. Okay, new students, okay, take this system granted, you'll be going through the unit 1 parallelly through the video lectures. Okay, fine. So omega n, as already given, it is a natural frequency of oscillations, radian per second. Zeta, it's damping of the system. K is a static sensitivity, the steady state connection between input and output, static sensitivity. Okay, that's your system. Now we are going to exit this second order underdamped system. It's underdamped, therefore damping is going to be strictly between 0 and 1. So first let me position where the pole of the system is before giving the inputs. What inputs we are going to play? We are going to apply is we are going to talk about only unit impulse response and step response only for the system. Only unit impulse and step only. We are not going through ramp response. I'll tell you how to plot the ramp response. It's not there in the syllabus. You won't get any problem for ramp response of a second order under damped system. But still we'll see how it will respond. Okay, already I said we are not going for the parabolic. Okay, we are not going for the parabolic. We didn't go for parabolic in first order. Yes, no parabolic analysis in second order. Same reason, whatever pinpointed in first order. Same reason why we should not apply parabolic for second order also, because error will grow to infinity. Okay, at time t equal infinity, that system is not capable of following parabolic input command, even with a little deviation. Okay. So only two response analysis we need to do. We are going to do in second order under damped system. One is unit impulse response, another one is step response. Only these two. Okay, but this is not easy. Even impulse response is also not going to be very easy, because the order is higher. Okay, so it's first order means only one pole, but here we are going to have two poles. That is going to complicate things. Even step response is going to be little complex, but still we need to derive and conclude. Okay, so only we are going to remember the formulations or conclusions for the responses. So we are going to get unit impulse response of the system, that is C of t for unit impulse input and C of t for the step input. That's all we are going to do for the second order under damped system. So let us understand the system better based on its pole locations. The system is the transfer function T of S, I can say shortly, that is C of S by R of S, that is equal to, it is K into omega n square by S square plus 2 zeta omega ns plus omega n square. Yes, where the poles are. Denominator roots are your poles. Therefore, the poles means to find the poles. Where the poles are means S square plus 2 zeta omega ns plus omega n square is equal to 0. Will give the poles. Okay, correct? Reading? Following right? Yes, one can respond.
Yes, sir.
Okay, yes. Then S is equal to minus 2 zeta omega n plus r minus root of b square, that is 4 zeta square omega n square minus S 4ac. So 4 omega n square you will get divided by 2a. That's where you get your roots. Correct? Hope you're following this. Then we get the roots. So minus 2 zeta omega n plus or minus. Then what is common? 4 omega n square can be taken out. Then out of the root, it becomes 2 omega n into root of zeta square minus 1 by 2 you will get, and this 2, this 2, this 2 will get cancelled. Okay, are you getting? Following
Yes,
right?
sir.
Yes, sir. Yes, sir.
Then, so I am getting two roots now. Where the roots are? S equal to The two roots are, we're getting this equation finally. S is equal to minus zeta omega n plus or minus omega n into root of zeta square minus 1. So we have a condition now. So this is the universal statement. This is applicable for any damping. Okay, this is applicable for any damping. But we have a boundary for our damping. The boundary is 0 to 1. When damping is strictly between 0 and 1, that's under damp system. So I'm looking for the pole locations of this under damp system. So based on that, I can quickly comment on stability and then conclude whether it is going to produce converging or diverging responses. Based on the damping itself, based on the pole itself, we can conclude. So then, if damping is between 0 and 1, what will happen to this factor, zeta square minus 1? If zeta is a fractional, that is less than 1, what about zeta square? For example, zeta equal to 0.8. What is zeta square then? It is going to become 0.64, correct? That means zeta square always going to be less than 1. When zeta is less than 1, that's an important conclusion. When zeta is less than 1, zeta square also going to be less than 1. If that is the case, this factor is going to be negative. Getting everyone? Yes or no?
Yes, sir.
Okay, if that is the case, you need to pull that minus 1 out. So let me write this as S equal to minus zeta omega n plus or minus omega n into root of, take minus 1, then write it as 1 minus zeta square. Okay, because of this conclusion, then minus 1 can be replaced by the parameter, okay, by complex number system. J square is equal to minus 1. J is imaginary, okay, representing imaginary. J square equal to minus 1. In mathematics, I square equal to minus 1. Okay, it's a complex number, fundamental. So then minus zeta omega n plus or minus, then you are taking minus 1, that is replaced by j square. Then j square is taken out of the root, which comes out as j omega n into root of 1 minus zeta square. And then I'm going to replace this by minus zeta omega n plus or minus a short representation of this known as another frequency of oscillation known as omega d is a damped frequency of oscillations. Frequency of oscillations damped out by damping factor. So we call it as damped frequency of oscillations. Omega n, natural frequency of oscillation. This is damped frequency of oscillations. We'll see. So that's omega d. So the important conclusion here is omega d is equal to omega n into root of 1 minus zeta square. Okay, and omega d. Okay, so zeta, and then you can play with omega d. When zeta equal to 0, what is omega d? Anyone? Because when it is under damped system, extremes are 0 and 1. Let me go for zeta equal to 0. What is omega d?
Omega n.
Omega n. Therefore, this omega n also known as undamped frequency of oscillations. No damping. Zeta equal to 0 is undamped condition. Undamped frequency of oscillations is also another name for omega n. Frequency of oscillations in radians per second. Okay, then zeta equal to 1. What happens to omega d?
0.
Extreme. Yes. Then no oscillations. Yes, that's good point. A critically damped system will have 0 oscillations. That's why, okay, we call it as critically damped condition. It's a critically damped condition. So critically damped system has 0 oscillations. Okay, so what is the damping which makes oscillation free response? Or the damping which is making the response oscillation free? That's a point known as critical point. So zeta less than 1 oscillations will be there. Zeta less than 1 oscillations will be there. Zeta greater than or equal to 1, there won't be any oscillations. You should not play for zeta greater than 1 because this equation is limited. When you played for this, only after taking this condition you played for this. And if zeta is greater than 1, that's the equation you need to use. So zeta, any zeta between 0 and anything infinity, one can use this equation. Okay, but this equation is limited use between 0 and 1 only. Under this condition only it is defined. Therefore, this equation is limited only for zeta value between 0 and 1. So we can use it for extreme cases, 0 That is undamped case and critically damped case we can use, but not greater than 1. Never try substituting zeta greater than 1 in this equation. That will make omega d itself complex. That will make omega d itself complex. There is no meaning for this. Therefore, this table is valid only for values between 0 and 1 only. Understood? Is this point clear?
Yes, sir.
And that is also giving a meaning why it is known as a critical point of damping or critically damped condition. So till the damping becomes critical, you will see oscillations in the response. By the time the damping is critical, there won't be any oscillations in the response. Even beyond that, that's a minimum damping needed to make oscillation free response. That's what called as a critically damped case. Better meaning of what is mean by zeta equal to 1, why it is known as a critically damped condition, where there won't be any oscillations in the output response. Omega d is the one talking about oscillations in the output response. We'll see that only by going through the response, we will see oscillations in response. So response means C of t only. Oscillations in output response you will get. Okay, that's what it means. Okay, output response will have oscillations of omega d. So omega d already defined. Omega d is damped frequency of oscillations. Radian per second, default unit. Okay, hope it is clear to everyone.
Yes, sir.
That's understanding on omega d. Now this is your ultimately the goal is to get the pole locations of the second order under damped system. Okay, so this is our second order system where the poles are now. So this is our system k into omega n square by a square plus 2 zeta omega ns plus omega n square. That's your transfer function. Okay, now where the poles are, we got denominator roots equal to s equal to minus zeta omega n plus or minus j omega d. Yes, where is the first pole? Where is the second pole? The pole is, yes, the poles are two poles. What is S1? Pole 1 is minus zeta omega n plus j omega d. That's a pole 1. Pole 2, second root, that is minus zeta omega n minus j omega d. Therefore, the poles are complex. The poles are complex conjugate. Agree? The poles are complex conjugate with negative real part. With negative real part. Negative real part means where the poles will fall. This is positive real. And this is negative real. And this is positive imaginary. And this is negative imaginary. Okay. Yes, therefore one pole will be falling here. Another pole will be falling here. This is minus zeta omega n. And this is plus j omega d. And this is minus j omega d. Is this clear, everyone?
Sir, yes.
Any doubts, Shaktivel?
No, sir.
Okay, yes. So that's where the poles are. Can you comment on the stability now itself? Can you comment on Bibo stability? The poles are on. The poles are on. Left side or right side?
Left side. Sir.
Therefore,
Stable
it is going to
conditions.
produce absolutely stable responses. So the responses will converge. Yes, now we are going for the responses. So we are going to apply an impulse input as well as step input. Then the response is going to converge. It is going to produce stable responses only. So C of t will be converging responses only because now we know where the poles are. Therefore, we can conclude the Bibo stability of the given system. Okay. We'll see how they are converging and how they are producing both. That means the output response is bounded even during transient. That's what it means. Okay, so that's what Bibo stability also says. It's not only talking about steady state output. Okay, due to that is a steady state bounded output due to the input bounded input. It's not only the analysis at steady state. It's also during transient. During transient also the output will be bounded. Okay, it will converge to a steady state. Okay, it may increase or decrease, that's not a question, but it is going to converge into steady state, that's all. Okay, so throughout the time from 0 to infinity, output will remain bounded. Output is going to have only finite values. Okay, it will never have infinite values, that's what it means. Hope this point is clear to everyone. Yes.
Yes, sir.
Okay, so now let me get few more information based on the pole location. So we are going to exploit that during our impulse and step response analysis. This is a pole. Let me take only this pole. A similar analysis can be done for this pole also. Let me draw a straight line connecting this origin and the pole. Draw a straight line connecting the pole and the origin. And we know this is equal to plus j omega d. And we know this is equal to minus zeta omega n. Now tell me, if I consider a triangle, I'm considering a triangle with respect to the angular position of the pole from origin. And this is your triangle, right angle triangle. Okay. Yes. Now tell me what is the adjacent of this triangle, and let the triangle has this as angle theta. That's theta is the angular position of the pole. Okay. Theta represents the angle, and that represents angular position of the pole with respect to origin of your S plane. Okay. In the S plane, what is a theta? Okay, created by your complex pole. This complex pole only I'm talking about now. This is a complex pole. What is a complex pole? The complex pole is equal to minus zeta omega n plus j omega d will create an angle theta. Can you tell me what is theta? You know the adjacent. What is the adjacent of this triangle and opposite of the triangle? Tell me what is the adjacent of the triangle with respect to origin. Origin is 0, 0. Okay. Yes. What is the adjacent? This length. What is the length? Adjacent length. Zeta omega n. Opposite length.
Omega D.
Omega d. Can you tell me what is theta now? Can you tell me tan theta? What is tan theta? Tan theta. Opposite by adjacent. Yes, what is that? Omega d by. Omega d by.
Theta omega D.
Theta omega n. So from this you know the theta, tan inverse of. Tan
Omega D
inverse
by
of omega d by zeta
theta omega.
omega n. Or you can also say theta equal to, what is omega d? Tan inverse of, what is omega d? Omega n into root of 1 minus zeta square by zeta omega n. Omega n will get cancelled. Then theta becomes tan inverse of what? Tan inverse of what? Root of 1 minus zeta square by zeta. Getting everyone? Yes. So the point is the angular position of the pole with respect to origin is simply depends on your damping factor. Remember, our damping factor of under damped system lies between 0 and 1. Hope it is clear. Yes.
Yes,
Yes,
sir.
right.
Yes.
Okay. Yes. So let me take that triangle alone, the damping triangle alone once again. Okay, this is omega d. Omega d is omega n into root of 1 minus zeta square. And this is zeta omega n. And this is our theta. I'm taking that triangle alone. Can you tell me what is hypotenuse of this triangle? This side. That is equal to root of adjacent square zeta omega n square plus opposite
Omega
square,
D
that
square.
is omega d square. Then if we equate this, then what do you get? Zeta square omega n square plus omega d square. Omega d is known as omega n into root of 1 minus zeta square. Then square it. You'll end up with omega n square into 1 minus zeta square. As a result, what is getting cancelled? What is getting cancelled? Zeta square omega n square will get cancelled with this. Agree?
Yes, sir.
What is the remaining within the root?
Omega n.
N square. Then what is the resultant?
Omega n.
Omega n. Therefore, this side is going to be omega n. Since this side is omega n, so let me scale down this triangle because omega n is common in all this sides. So let me eliminate omega n in all this side. Then this is going to be 1. Getting everyone? Therefore, this triangle now scale down because I'm scaling it down because I'm removing omega n. This is 1. This is zeta and this is root of 1 minus zeta square and this is your theta. Then once again, what is tan theta? What is tan theta?
Of it.
Root of 1 minus zeta square by zeta. So theta equal to once again tan inverse of root of 1 minus zeta square by zeta. Same theta we are getting again. Getting? All of you getting this point?
Yes, sir.
So then this may be a hard theta to remember. So let us have a easy theta, a theta easy for our memory. So can you tell me from this what is sine theta? Easy. Opposite by hypotenuse. Correct? Root of 1 minus zeta square by 1. Cos theta. Cos theta.
Zeta.
Adjacent by hypotenuse. Correct? Yes or no? So which one is it? So I have given sine theta, I have given cos theta, I have given tan theta. Which one is easy to remember?
Tan theta.
Tan theta. This is tan theta. Tan theta is root of 1 minus zeta square by zeta. Yes, which expression is easy to remember? All of you getting? The simplest of the three.
Cos theta.
Cos theta. Therefore, that's your theta to remember. Cos theta equal to zeta. Theta equal to cos inverse of zeta is the best expression to remember, but still we'll be using this identities sin theta and cos theta later. If required, sometimes we'll be using tan theta as well. Okay, so this triangle we call it as damping triangle, a triangle function of damping factor only, call it as damping triangle. And this triangle we got it from angular position of your pole, not to forget this fundamental. Okay, so this is omega n. Already we concluded. Okay, so that's your original triangle. We downsized it and we made it only function of a damping. Theta is only function of your damping. So this is a conclusion here. Because of that, here omega n is getting cancelled. So better you can downsize your triangle and make it only function of your damping factor. So therefore, the angular position of this complex conjugate poles. Okay, this is for this. And you can try this for this pole also. This pole also you can try. And that angular position also going to be the same. Theta, it will be the same expression for this pole. If you try, that is minus zeta omega n minus j omega d. Okay, that is the second pole of your complex conjugate structure. Okay, minus zeta omega n minus j omega d. This is also going to have the same theta. The focus is on this positive imaginary, negative real. Okay, this is negative imaginary, negative real. Okay, the theta will be same. Suppose if given. Okay, that's how we need to play. So these are the important conclusions. Now we'll be using this later in our underdamped impulse and step responses. Any doubts till now? Any
Yes.
doubts till now? Clear? We'll be using this. Okay. So now let us begin unit impulse response of underdamped second order system. R of t equal to del of t. Your system, numerator k into omega n square, denominator a square plus 2 zeta omega ns plus omega n square, and the output is C of t. The goal is to find C of t. Yes. That's a response. That's a reaction of your underdamped second order condition here. 0 to 1 is a condition. And you know the pole location, one pole here, another pole here roughly. Okay. Yes, we need to get the response. We know C of S. We know R of S. R of S equal to Laplace of unit impulse. What is that? 1. Then what is C of S? C of S equal to your R of S into the transfer function. Just multiplication. Therefore, R of S equal to 1 means your C of S is going to be the transfer function itself. This is your transfer function T of S. Therefore, C of S is equal to same as your transfer function K into omega n square by A square plus 2 zeta omega ns plus omega n square. That's your C of S. The goal is to get C of T. Easy? Following right?
Yes.
So C of S is equal to K into omega n square by A square plus 2 zeta omega ns plus omega n square. Now I need to find out C of T. Yes, how to? I need to apply Laplace transform inverse. The goal is to get C of T. So we need to have identity. So we know Laplace of u of t is equal to 1 by s. We know Laplace of e power minus at into u of t is 1 by s plus a. We know identities, but we need to cover this. Okay, we need to cover this. But we know it's underdamped system that is going to have oscillations. We know it is underdamped system. It is going to have oscillations at what frequency? Omega d. Omega d will be finite. That is omega n into root of 1 minus zeta square. So it is going to have oscillations. So therefore, we need identities as a function of oscillations. So then begin identity of Laplace of sine omega t. Yes, that is going to have an oscillations at omega radian per second. Laplace of sine omega t. Laplace of sine omega t. That will help us. Anyone? Laplace of sine omega t.
Omega by S square plus omega two.
Yes, take it granted. That's omega by a square plus omega square. Laplace of cos omega t.
By S square plus omega square.
S by a square plus omega square. Yes, that's fine then. It is s square plus omega square in the numerator, but what we have is s square plus omega n square. Along with that, we have another factor. So the denominator should be of this form. Then we can directly apply Laplace transform inverse and find out C of t. So it is not helping us. So denominator should not have this s term. So then we can use this identities. So denominator is having this. And this is going to help you. Okay, this is Laplace of a function u of t. Otherwise, from this can you generalize? Laplace of u of t is 1 by s means Laplace of e power minus at into u of t is 1 by s plus a. Can I say Laplace of a function is f of s. Laplace of e power minus at into f of t can be remembered as f of s plus a. That's identity. All of you getting? That's what these two are proving. Yes or no? So Laplace of u of t is 1 by s means Laplace of e power minus at into u of t is wherever you got s, replace it by s plus a. That's what it means. F of s, wherever you got s, replace it by s plus a. Easy? All of you getting? Following right? Yes or no? So yes, we need not remember all the identities. Still some logical play. With that, can you tell me Laplace of e power minus at into sine omega t? Okay. Anyway, we need to remember, but remember with the logic. Laplace of e power minus at sine omega t. Sine omega t Laplace we know that is this, and use this identity. Laplace of f of t is f of s means Laplace of e power minus 8 into f of t is going to be f of s plus a. That means wherever you have s, replace it by s plus a. Then what is the identity? Remember this. What is the identity here? Omega by anyone? Omega by
S plus E the whole square.
whole square plus omega square. Logical? Getting everyone? Following right?
Yes, sir.
So similarly, can you say the final identity? Laplace of e power minus at into cos omega t. Laplace of e power minus at into cos omega t. Yes, is equal to
S plus A
s plus a by s
divided by
plus a
S plus
whole
A whole
square
square
plus omega
plus
square.
omega.
Easy? Easy everyone? Yes, that's what we need. So now tell me whether our denominator can be made something like this. It is s plus a whole square plus omega square. We can modify our denominator to this form. Then we can do Laplace inverse. Okay, no partial fraction expansion involved. Only thing is that we need to modify our C of s suitable for Laplace inverse. Then only we can get into time domain. So we are lagging in identities. That's why I introduced Laplace of sin omega t, Laplace of cos omega t. With this, after exploiting this property of Laplace, then we know what is this Laplace and what is this Laplace. So now denominator is matching. So it's our job to modify this denominator in the form of s plus a whole square plus omega square. That's how we need to modify. Hope you got the idea. Yes, kidding? All of you. The job is I'm going to modify the denominator. This is your numerator, something in numerator. Then the denominator I'm going to modify as s plus a whole square, some x square, something like that. Then I can apply this identity. Otherwise, it is not possible. Hope you're getting, all of you? Following right?
Yes, sir.
Okay, yes. Now let us modify C of s suitably for Laplace transform inverse. So this is C of s, that is equal to k into omega n square by a square plus 2 zeta omega ns plus omega n square. I need to modify this. And we remember a square plus 2 zeta omega ns plus omega n square equal to 0 as given two poles. Equal to 0 given two poles. What are the poles? One pole is this, another pole is this. Correct? Yes or no? All of you getting? One pole is this, another pole is this. Shall I write this in pole factor form? Shall I write this in pole factor form? Equated to 0 given two poles. Shall I write this as, and the two poles are s equal to minus zeta omega n plus j omega d. Another pole is s equal to minus zeta omega n minus j omega d. Shall I write it in pole factor form as s plus zeta omega n minus j omega d is the first pole factor. Another pole factor is s plus zeta omega n plus j omega t. Shall I write it? Any mistake I'm committing? If you equate this to 0, what you will get? This is the first pole, this is the second pole. All of you getting? Yes or no?
Yes, sir.
So this is a pole factor form. This can be written in the pole factor form. Now the pole factor form resembles this is A and this is B. This is A, this is B. This resembles A plus B. This resembles A minus B. So what is A plus B into A minus B?
A square minus B square.
minus b square. But j square is there. J square will make another minus. That is going to become plus. Then what is the resultant? Omega d square. What is the point to prove here? A square plus 2 zeta omega ns plus omega n square is actually equal to s plus zeta omega n whole square plus omega d square. If you write this way, then it's easy for the Laplace inverse. That's a point. Therefore, I can write C of s is equal to k into omega n square by s plus zeta omega n whole square plus omega d square. Now it is almost in the form of what is given here. S plus a whole square plus omega square form I modified. But only thing is that numerators, do we have s plus a in the numerator? If it is s plus a, I can make it to the cos form. If it is a constant, I can make it to the sine form. What is in the numerator? Do we have s plus a in the numerator? What is it there in the numerator? Only k into omega n square. Only constant is there in the numerator. No s plus a. Therefore, we can't make it to the cosine form. We can't make it to the cosine form because we are looking for s plus a in the numerator. That is not there. So only other choices we need to make it only in the form of sine form. So that need to have omega. But what we have here is omega d square. Therefore, we need to have omega d in the numerator. So multiply and divide by omega d. A small adjustment. Clear everyone? Following? Yes or no?
Yes.
Yes. Is it clear?
Yes, sir, clear.
Okay. Then go ahead. Then C of s can be written as, so k into omega n square by omega d. Take it as a common. Rest is omega d by s plus zeta omega n whole square plus omega d square. Now this term is ready for Laplace inverse. Rest is the constant you can take. Yes, apply Laplace inverse. Now C of s can be written as k into omega n square by omega d. Yes, once again copying it, omega d by s plus zeta omega n whole square plus omega d square. Yes, apply Laplace inverse. Laplace transform inverse resulting in C of t is equal to, yes, parallelly, what is this omega d? What is omega d? Omega n into root of 1 minus zeta square, then the square n, omega n will get cancelled. So C of t, this constant becomes k into omega n by root of 1 minus zeta square. Then Laplace inverse of this will be, Laplace inverse of this will be, this is resembling Laplace transform inverse of what? X by s plus a whole square plus x square. That is equal to a power minus at into sine xt. Getting? Yes. Getting right? Yes or no? Where x is representing omega d, a is representing zeta omega n. Shortly. Okay, so therefore this is e power minus zeta omega nt into sine omega dt into u of t. Getting all of you? Yes or no? Following right?
Yes.
That's all. Yes, that's your unit impulse response of a standard second order under damped system. Okay, clear? Where omega d is equal to omega n into root of 1 minus zeta square radian per second. It's finite oscillations. So let us have a meaning for this. Till this point, any doubts? Anyone? Hope everyone is clear about this. Any doubts?
No.
Okay, yes. Then C of t. This is your system. K into omega n square by a square plus 2 zeta omega ns plus omega n square. Excited by all of t, that is equal to del of t, producing the response C of t. Yes, you can also never get surprised if someone is giving a transfer function like k into omega n square by s plus zeta omega n whole square plus omega d square. That's really a helping hand. He already modified your denominator to the suitable or desired form. Then it's easy to get C of t. So C of t, that's a perception of the second order in terms of your A and your omega d at which it is going to oscillate. C of t equal to k into omega n by root of 1 minus zeta square into e power minus zeta omega nt into sine omega dt. And the poles of the system is here. The real part is minus zeta omega n and it is plus j omega d. It is minus j omega d. Okay. So that is going to be part of your transient part because of your pole location. So whenever you have, for example, you have pole here, for example, this is minus 2 and this is for example plus j4 and this is minus j4. Can you tell me quickly what will be the transient part? What will be the transient part for this setup? Imaginary is, sorry, real is minus 2, imaginary is 4. Then what will be the transient part? E power minus 2t into sine 4t. Like that, you will get the transient part for the structure. Getting all of you? Yes or no?
Yes.
That's what it means. How the pole influence your transient part. If it is a single pole, for example, something like this, the pole at minus 2, what do you say? The transient part will contribute e power minus 2t. Similar to that, if the pole is minus 2 plus j4 and minus 2 minus j4 means then the transient part will be e power minus 2t. Along with that, you will get sinusoidal oscillations at where the complex or imaginary value, at this imaginary value, it will produce oscillations. That's what it means. Okay. All of you getting this point? Clear? Following right?
Yes, sir.
Now let us plot the unit impulse response C of t. Plot the response C of t. Namesake into u of t, you can say. Okay, that means that it is the response valid for t greater than or equal to 0 second. Can you plot it? Can you plot the response? To make sense, let me write this way. E power minus zeta omega n t into k omega n by root of 1 minus zeta square. We'll see how this is making sense. This is an exponential decay function. This is a constant sinusoidal oscillations with this as the peak value, like Vp sine omega dt. That's a peak. Okay, so you can take it as like a peak voltage. Okay, or a sine omega t, like that you can treat. So this is a sustained oscillations at an amplitude k omega n by root of 1 minus zeta square. Hope you understand what this Vp refers, peak voltage. So it's a voltage signal, something like that. Okay, so similar to that, okay, pure sinusoidal component it is with an amplitude k omega n by root of 1 minus zeta square. That's peak of k omega n by root of 1 minus zeta square for better understanding. and this is Vp, and this will be minus of k omega n by root of 1 minus zeta square is the amplitude. Okay, and oscillations at omega t, that is this component, that is multiplied with an exponential decay going from 0 to 1 for time t equal to 0 seconds. This is evergreen. This is always existing, but this one begins with a value of 1 and then decaying to 0. How long will it take to decay to 0? Transient part alone. Transient part will take how much time to decay? Transient part will settle, will converge to steady state at what time? By the time it approaches e power minus 5, because we know e power minus 5 equal to 0. E power minus 5 is 0, means 0 into anything is 0. Therefore, the total response will become 0 when you get e power minus 5. When it is going to happen? E power minus zeta omega nt is equal to e power minus 5, means your c of t will vanish. So till that point only you're going to see the oscillations in the response. Yes, that's how it is going to be. So till that point, what is that? Zeta omega nt equal to 5. That means zeta omega nt equal to 5 means t is equal to 5 by zeta omega n. That is your settling time. Approximately at 5 by zeta omega n, it will converge to 0. Getting everyone? Getting all of you?
Yes, sir.
Yes. So till that settling time, you will have decaying oscillations. This product is nothing but decaying oscillations. That's your response. The unit impulse response of a second order underdamped system is decaying oscillations. It's a decay multiplied by sustained oscillations. Okay, decaying oscillations. Plot it now. Anyone having doubts? Anyone having doubts? Clear? Is it clear?
Yes, sir.
Okay, now let us plot C of t. Initially no response, it is 0. This is the envelope of e power minus zeta omega n t. So the interesting point is this envelope, that is exponential decay, is getting multiplied with positive off cycles as well as negative off cycle. Therefore, the positive and negative off cycles are getting the envelope of your exponential decay. So let this is an exponential decay. So then your oscillations are guided by this exponential decay envelope. So the response will be something like this. Getting everyone? Getting all of you? Oscillations died out. This is your time, settling time, till which you will see the decaying oscillations. After that, there won't be any oscillation seen because e power minus 5 is 0. Okay? Easy. Easy everyone. All of you getting this?
Yes, sir.
It will show some visible cycles of oscillations. We don't know how many cycles of oscillations, roughly it is sketched. We'll talk about the number of visible cycles of oscillations. So this is your transient part, transient response. And this is your steady state response. Comment on stability. Whether the response becomes unbounded anytime? No, right? Because oscillations are decaying, so they are converging oscillations. Oscillations converge to finally zero. That is response at steady state equal to zero. Initial response for t less than zero, c for t less than zero also equal to what? Zero. Response begins from zero and having some oscillations, but that oscillations is not going to be a great number. This is your amplitude, and this amplitude is going to be when t equal to zero. T equal to zero, t equal to 0, anyone substitute t equal to 0 in this. T equal to 0, e power minus 0 you will get. But at the same time, sine 0 is 0. It's enough to make entire function 0. Therefore, the response, unlike your first order system, which is beginning with k by tau, this is beginning with 0 only. Okay, unlike your first order system, the c of t of unit impulse response of second order, it doesn't begin with a finite value, it is also beginning with 0. That's a point because sine 0 is 0. Okay, yes or no? Whenever omega dt touches, whenever omega dt touches n pi, oscillations will touch 0. Whenever omega dt touches n pi, oscillations are 0. Remember, sin n pi equal to, sin n pi is equal to, n can be an integer. N is 0, 1, 2, 3, 4, whatever it is. N equal to 0, first time, oscillation beginning, pi 180 degree. Yes, wherever. So after 180 degree, it is 0. After 360 degree, it is 0. After every pi, it is 0, 0, 0 response. Because sine 0 will make the response touching this 0 point. Getting everyone? Getting this point? Clear? So that's how a second order underdamped system produces decaying oscillations. So this is a point to remember finally. So we have a second order system excited by del of t. Shortly, that's our conclusion. Second order underdamped. Then the response excited by impulse input. Then the response is exponential decay. Like this. Okay, that's all. Starting from 0, ending at 0. That's what we need to remember. Okay, clear everyone? And settling at what time? 5 by zeta omega n seconds. Simple. Understood now? Okay, how much time it takes to deduce a unit impulse response itself in a second order underdamped system. Is it clear? Complex or easy? Complex or easy? It's where we
Easy.
started. Yes. Okay. Yes. All fundamentals. We were lagging in identities, so we brought them into the picture. Then we adjusted C of S so that we can apply Laplace inverse suitably. Okay, and then get into time domain. Then after getting the time domain response, we want to understand how it will graphically give the response. Okay, with respect to time from 0 to infinity. Okay, that is simply indicating a product of exponential decay with the sustained oscillations. So we concluded that product as a decaying oscillation. With that knowledge, we're able to plot the response, impulse response C of t. Okay, that's what we need to remember. Expression has to be remembered, and the corresponding graph has to be remembered for the unit impulse response. Okay, that concludes unit impulse response of a standard second order. So let us begin the next one. Yes. If you have any doubts, we can discuss. Yes, Sandil.
No doubt, sir.
Shaktivel following right.
Yes, sir. Following.
Swarna following right.
Following, sir.
Akshaya? Anyone having difficulty in following these concepts? Okay. Yes, then we'll begin with the step response. Step response of second order or underdamped second order. R of t, we're looking for C of t, zeta strictly between 0 and 1. Same system, k into omega n square by a square plus 2 zeta omega ns plus omega n square. Okay. R of t is a into u of t. We are applying the input. Already the step is well defined. At time t equal to 0 second, the input is changing from 0 to magnitude a. This is what we call as step size a. A is step magnitude or step size. The goal is to find C of t. Then C of t is known as the response. Response of the system for a step input, shortly known as step response of the underdamped second order. This is talking about C of t only. Okay, we need to find C of t. Okay, so find C of t now. Okay, whatever the identities we made, okay, we have gone through will be helping us. Okay, once again. What is R of S? Well known. Already we have used it in first order. A by? Yes, correct. Laplace of u of t 1 by s. So R of s is a by s. So then C of s. The goal is to get C of t. So first get C of s. C of s equal to R of s into your transfer function. Okay, R of s is known, T of s is known. Therefore, C of s is equal to R of s into T of s. That is equal to R of s is a by s. T of s is k into omega n square by a square plus 2 zeta omega ns plus omega n square. Okay, yes, we need to apply partial fraction expansion. Okay, it's not easy. Inverts like our unit impulse response. Okay, then C of s can be written as, let me take a k as common. Rest I can keep it within the brackets, omega n square by s into a square plus 2 zeta omega n s plus omega n square. Okay, fine. So apply partial fraction expansion only for this. Then I can write it as ak into, let me write it as a by s plus. So this is second order. I can't easily split it into two parts. Let me write it as bs plus c. Another way of partial fraction for second order where I can't split it, okay, into two parts. If it is a square, what we did earlier, a by s and b by s square, like that we did. Okay, so otherwise you can write a plus bs by a square also we can write same way. Okay, so it is a square plus 2 zeta omega ns plus omega n square. Okay, numerators having the partial fraction constants b and c. Yes, that's how this term can be partial fractioned. This term can be partial fractioned into this. Then the goal is to find the partial fraction expansion constants a, b, and c. Okay, we'll find them. Okay, then we'll adjust the denominator so that, or we'll adjust the each term, okay, component of this C of S, so that we can apply Laplace transform inverse and quickly get into time domain. That's a plan. So let us do partial fraction expansion first. It's omega n square by S into A square plus 2 zeta omega ns plus omega n square, that is equal to A by S plus Bs plus C by A square plus 2 zeta omega ns plus omega n square. Okay, now after taking LCM, left side will be only omega n square, right side will be A into A square plus 2 zeta omega ns plus omega n square plus Bs plus C into S. Are you getting, everyone?
Yes, sir.
Then set S equal to 0 in the equation. What do you get then? Left side is omega n square. Right side is S equal to 0. A into omega n square alone remains. This S equal to 0 will switch off B component and C component. So I can go for A. So that result in A is equal to 1. Easy? Easy?
Yes, sir.
Then compare A is known. Compare S square coefficients on both sides. Compare S square coefficients on both sides. No S square terms in left hand side, it is 0. Right hand side, S square terms. A is the S square term, A square. So coefficient of S square is A plus no other S term here, no other S square term here. And here Bs into S will give you Bs square. So B is the term. C into S is only S term, not S square term. Therefore, comparing S square terms on both sides, that gives another equation 0 equal to A plus B. So then from this B is equal to minus A. Therefore, B is equal to minus 1. Getting? Getting all of you? Yes?
Yes, sir.
Clear? Okay. Then compare finally S terms, coefficients of S terms. Left side no S term, right side S terms please. A into 2 zeta omega n is the S term. Another S term is C into S, correct? So from this A is 1 already, therefore C is equal to minus 2 zeta omega n. Getting? All of you following right?
Following, sir.
So A is 1, B is minus 1, C is minus 2 zeta omega n. Yes, little complex, not easy because we need to go through partial fraction expansion as well. So now let us replace A, B and C in this equation. In this equation, we'll substitute A, B and C values. Let me write C of S first. It is AK into A by S plus BS plus C by A square plus 2 zeta omega n S plus omega n square. Tell me what is A? What is A? 1.
1.
So replace A by 1. B minus 1. B is replaced by minus 1. So minus S I can say shortly. Then C is replaced by minus 2 zeta
minus 2 zeta omega n.
omega n. So therefore I can replace it by minus 2 zeta omega n. Agree everyone? Easy? Easy, right?
Yes, sir.
Then C of S can be written as AK into 1 by S is ready for Laplace inverse. Let me take minus common. If I take minus out, what is the remaining here? S plus 2 zeta omega n will remain. If I take minus common, then let me write it as S plus zeta omega n with the denominator minus zeta omega n with the same denominator. Is it okay? Is
Okay.
it okay? S plus 2 zeta omega n is there in the numerator. I'm writing it as purposely S plus zeta omega n and zeta omega n, a preceding minus minus minus. Okay, that's all. Denominator same. A square plus 2 zeta omega ns plus omega n square. Here also it is S square plus 2 zeta omega ns plus omega n square. Any doubts? Is it okay? Clear?
Clear, sir.
Then next step, let me write C of S equal to AK into, I'm not leaving this part also for your practice. Okay, so let me prove it once. Then let me write it as S plus zeta omega n, the whole divided by S plus zeta omega n whole square plus omega d square. Already we know this identity. This can be modified as this. Already proved. Here also let me write it as zeta omega n by S plus zeta omega n whole square plus omega d square. Now you know this is ready for Laplace inverse. It's in the form of, it is going to give, if you apply Laplace inverse, it will give e power minus zeta omega nt into cos omega dt. Getting everyone? Yes or no?
Yes.
So this is going to be in the cos form. Okay. So it's ready for Laplace inverse. What about this? No s plus a term in the numerator, therefore only the constant is there. So to make it better, it is going to give sine form only. So for that we need omega d in the numerator. Omega d is not there in the numerator, so let me multiply and divide by omega d. So multiply by omega d, divide by omega d, that's all. So now let me write C of s is equal to ak into 1 by s minus s plus zeta omega n by s plus zeta omega n whole square plus omega d square minus, what is there? Zeta omega n by omega d. What is omega d? And here omega d is omega d by s plus zeta omega n whole square plus omega d square. Correct? Getting everyone? Following right? Yes or no?
Yes, sir.
Then omega d can be replaced by omega n into root of 1 minus zeta square. Then this omega n will get cancelled. So then the final step can be written as C of s is equal to ak into 1 by s minus s plus zeta omega n by s plus zeta omega n whole square plus omega d square minus, what are the remaining? Zeta by root of 1 minus zeta square remains. So zeta by root of 1 minus zeta square into omega d by s plus zeta omega n whole square plus omega d square. Okay, that's all right. Getting? Okay. Yes, apply Laplace inverse now. C of t is equal to ak into 1 by s u of t minus this Laplace inverse s plus a form. So e power minus zeta omega nt into cos omega dt into u of t. Okay, fine. Minus this one zeta by root of 1 minus zeta square. Is this form Laplace inverse of this? Is e power minus zeta omega nt into sine omega dt into u of t. Clear? Is it clear, everyone?
Yes.
Yes, simplify. further C of t, ak is common. Let me take u of t also common. 1 minus e power minus zeta omega nt. Let me pull out root of 1 minus zeta square as well. So tell me what is the remaining into u of t. U of t pulled out. So then here in this term, I'm pulling this e power minus zeta omega nt. Here also e power minus zeta omega nt. Minus also pulled out. Minus is pulled out. So minus pulled out, e power minus zeta omega nt pulled out. Along with that, I'm pulling out this factor as well. So if I pull out this, which is non-existing in the first term, therefore I can write the first term as root of 1 minus zeta square into cos omega dt. Agree everyone? Yes? Following? Yes or no? Plus this is already pulled out, this is pulled out. So zeta into sine omega dt. Yes, that's all. Is it okay for everyone? Yes or no? Following or not?
Yes, sir.
Following, sir.
As per our damping triangle, this is our theta. This is our 1. This is our root of 1 minus zeta square. This is our zeta. We remember sine theta. What is sine theta? Root of 1 minus zeta square. Cos theta?
Zeta.
Zeta. Yes. Replace this by sine theta. Replace this by cos theta. Then you will end up with C of t equal to ak into exploiting the damping triangle 1 minus e power minus zeta omega nt by root of 1 minus zeta square. This is sine theta cos omega dt plus cos theta sine omega dt into u of t. Yes, now it gives you an identity. Sin a cos b plus cos a sin b. This reduces to sin a plus b. All of you getting? Yes or no? Following right?
Yes, sir.
Yeah, simplify. That's a final step. Therefore, the response C of t simplifies to ak into 1 minus e power minus zeta omega nt by root of 1 minus zeta square into sine omega dt plus theta into u of t is the simplified version, should be remembered. That's your step response of standard second order system, where omega d is omega n into root of 1 minus zeta square radian per second. Theta equal to cos inverse of zeta in degrees it is. Okay, that's all. That's all right. Provided zeta strictly takes values between 0 and 1. It's under damped system. Correct? Following everyone?
Yes, sir.
Now, what will be the plot of this response? What will be the plot of this response? C of t. Time t equal to 0, what's the response? 0. No input, no output. Time t equal to 0, response is 0. Time t equal to infinity, what is your response? Time t equal to infinity. E power minus infinity is 0. Then the response will touch. Will attain what value?
-5.
A time t equal to infinity, e power minus infinity is 0. That means the entire transient part will die out. Getting Akshaya? E power minus infinity is 0. So entire transient part will die out. Only 1 will remain. And 1 into ak alone will remain. So therefore the response will reach what value? What value? Ak. Getting everyone? All of you getting this?
Yes, sir.
And this transient part resembles the unit impulse response. The transient part resembles unit impulse response. Correct? See this e power minus zeta omega n t into sin omega t t. Okay, something like that. That is going to die out. So transient part is dying oscillations. So those dying oscillations are subtracted from 1. That's what this means. These are dying oscillations. These are decaying oscillations. The transient part is decaying oscillations. You are subtracting the decaying oscillation from 1. That is your resultant response. So oscillations will decay finally, and finally the response will reach AK. So the response is going to be something like this. So it's going to be again a decaying oscillations, but not around 0. It is around AK. Oscillations are going to be around the final value, that is AK. So this is how you're going to get oscillations. So then the response will look like this. That's your second order under damped system step response. Getting everyone? Getting? All of you getting this? And this frequency of oscillations is omega d. Okay, so omega n given, damping given means we can find out oscillations. Then the system is going to settle at once again at 5 by zeta omega n seconds. That's your settling time. Till that you have transient response. This is your transient period. And beyond that time, it's your steady state. Response. This is transient response. Is this clear to everyone? Okay.
Clear.
So we'll get the time domain performance specs soon. For the because step is the regulatory control command, input command, so it has a meaning. Okay, a second order system excited by a constant command, regulatory command. So we need to analyze so many performance specs. Okay, for the system, we'll do that later. Okay, right? Today only we are going to do it. So we are going to conclude the total response analysis of time domain response analysis of our second order under damped system. First we excited by a unit impulse input. Now we are exciting it by a step input, not unit step. If it is unit step, A will be equal to 1. That's all. So if it is a standard first order system, keep the K in action because you know the system is going to settle at A and K. But many control system textbooks, okay, even the international authors, they will take K is equal to 1. They will take A is equal to 1. If someone gives a different A, someone gives different K, you may not conclude properly. That's why I play with A and K in both first order as well as second order. That's very important. Getting everyone? Is it clear?
Yes, sir.
Then we'll transfer this fundamental into a standard second order control system loop, a closed loop control system. Let me introduce. Similar to the first order closed loop, now we'll have a standard second order closed loop control system. Standard second order closed loop control system. Input R of t. That's your G of S. That's your error signal E of t. Unity feedback. It is the output response E of t. unity feedback. H of s equal to 1. G of s is equal to, let me refer this as G of s. G of s, the open loop transfer function or forward path transfer function is k is not there. So k is equal to 1. So omega n square by s into s plus 2 zeta omega n. That's your G of s, where zeta is a parameter strictly taking values between 0 and 1. Yes, that's your standard second order closed loop control system. Can you tell me what is the transfer function? Output is C of s, input is R of s. Can you convert this into a single box? And its transfer function is C of s by R of s. Yes. Yes, already you know h of s equal to 1. G of s is given, means you know how to find the transfer function. Therefore, C of s by R of s for the system you know already for a negative feedback. As per the negative feedback theory, G of s by 1 plus G of s into h of s. Clear? Can you get the transfer function now? C of s by R of s is equal to, yes. What do you get now? G of s omega n square by s into s plus 2 zeta omega n, the whole divided by 1 plus omega n square by s into s plus 2 zeta omega n into 1. As a result, after taking LCM, s into s plus 2 zeta omega n will vanish. Remaining, the numerator becomes omega n squared. Denominator is s into s plus 2 zeta omega n plus omega n square. Is it clear to everyone?
Yes, sir.
Expand your denominator. Finally, expand your denominator. Then if you expand it, then it becomes omega n square by, expand it, s square plus 2 zeta omega ns plus omega n square. Now it is resembling this only. It is resembling this only. Correct? But the only change, denominator is same. But what is the only change? The numerator only. Here the numerator is k into omega n square. And here the numerator is. Here the numerator is what?
Omega n square.
Yes, what is k?
1.
1. Yes, that is nothing but our C by R is equal to 1, because the loop is having one integrator, that is this 1 by S. This 1 by S is, system is having an integrator that is going to make your output 0 at steady state. The output 0 means whatever your input command, that is going to be C. That is the one going to make C by R is equal to 1. So K is nothing but the static sensitivity change in output by change in input command, that is equal to 1. That's what it means. Whatever the change happens in input, that is getting reflected in the output. So K once again gives a better meaning. So C is equal to K is equal to 1 represents your output is going to follow your input. Error is going to 0 once again in this closed loop control system. Desirable act? Yes or no?
Yes, sir.
Okay, now tell me what is C of t in this. K is equal to 1 only, that's all. Okay, so therefore, if R of t is equal to A into U of t in this, that's a standard second. Let me do it once again with one more. Okay, that's your system. K is equal to 1. Let me take that way. So that's a conclusion. Now for the system, if R of t is equal to del of t, then it is going to become unit impulse response analysis in a standard second order closed loop control system. This is your structure. So for the structure, going with unit impulse input. Then you know your C of t. What is C of t? C of t is equal to k into omega n. K is 1, therefore omega n by root of 1 minus zeta square into e power minus zeta omega nt into sine omega dt into u of t will be your impulse response for this closed loop structure. Clear? Then the response will begin from 0, then it will oscillate and then will settle to 0. That's your unit impulse reaction for this closed loop structure. Okay, correct? Clear? Yes or no?
Yes, sir.
Then for the same structure excited by a step input a into u of t, giving step change now going from 0 to a, and k is equal to 1, and we know our c of t. C of t is equal to ak becomes a into 1 minus e power minus zeta omega n t by root of 1 minus zeta square into sine omega dt plus theta into u of t is the response. Then if you plot the response, then the response begins from a and then oscillates and settles to a. Getting? Instead of ak, it is going to settle to a. That's what means c by r is equal to 1. Here also it is c by r is equal to 1, but r is equal to 0 by the time t greater than 0 because it's impulse, okay, and output is also going to become 0 at steady state. Here input is a at steady state, that is for t greater than 0 forever. Output follows your input, therefore error becomes 0 here. Okay, so here error is equal to 0, making sense. Steady state error. Here also error is equal to 0 because at steady state by time t equal to infinity input is 0, output is also what? 0. Then error is also 0. That integrator is responsible to make that error 0. Here is also the integrator is responsible to make the error 0 for step input. But if you apply a ramp input, error won't go to 0 for a reason. We'll see that in steady state error analysis in one more subtopic later in this unit. Is it clear? So we got the fundamentals of unit impulse response as well as fundamentals of step response to the standard second order closed loop control system. That's a purpose. So hereafter, if the structure is resembling a second order, you know how to recollect your formulation. Is it clear? Is it clear?
Yeah.
Anyone having doubts? Anyone having doubts? Okay, yes, we'll address few examples, okay, before getting into time domain performance specifications, okay. First example, unity feedback closed loop control system. It is C of S, input is R of S. The question is the value of K, such that the damping in the given closed loop control system is equal to 0.2. Find the value of K such that the damping in the given closed loop control system is equal to 0.2. Yes. So K is going to influence your damping. I want the damping to be set to 0.2 means find the value of K. Yes. How to proceed? Find C of S by R of S. Let it look like, let the denominator look like a standard second order. You'll get some numerator. Denominator should look like a square plus 2 zeta omega ns plus what? Omega n square. Then you can take a call. Getting? Yes, find the transfer function. Then compare with the standard second order. So C of S by R of S is equal to G of S by 1 plus G of S H of S. Exploiting this, C of S by R of S becomes, yes, quickly can you say, K by S into S plus 4 by 1 plus K by S into S plus 4 into 1. So then you can bypass the step and then quickly you can say, so K is there, it's K divided by S into S plus 4 plus K will be the transfer function. By habit, you will start writing this later. Okay, once you get the command, you can bypass the step. But anyway, I'm suggesting you to write the step also so that you won't commit any mistake later. Okay. Yes, that's your transfer function, which resembles what? Which resembles what? What is there in the numerator? What is the denominator? Expand your denominator to a square plus 4s plus k. Numerator is k. This resembles only omega n square by a square plus 2z 2 zeta omega ns plus omega n square. That's all. But remember, forget your k. Your k is there. Your k is static sensitivity. That is our k is static sensitivity. So replace that k by k1. Okay, because he is using k. The moment designer is using k and avoid our k, use k1 as our standard transfer function static sensitivity. So that k1 is equal to what? 1 in the system. And then conclusion omega n square is equal to k is the first conclusion. Yes or no? Yes or no?
Yes.
Then 2 zeta omega n is equal to what?
4.
4 then. Okay, yes then. So 2 zeta omega n equal to 4. Therefore, what is the problem? What is the value of k so that your damping is set to 0.2 means set zeta to 0.2 means 2 zeta omega n becomes 0.4 omega n. That should be equal to 4 means what is omega n? What is
10.
omega n? 4 by 0.4. What is that? 10 radian per second. If omega n is 10 radian per second, we have k is equal to omega n square. Therefore, k is equal to omega n square, that is 10 square. K is equal to 100 will satisfy the requirement. Getting everyone?
Yes, sir.
So try this once. That's a simple verification. When k equal to 100, what happens in the loop? 100 by s into s plus 4, right? That's your system. Yes. Under the closed loop. So you can take only denominator. Shortly, one can play like this. 1 plus g of s h of s is the denominator. Equate this to 0. That is resembling a square plus 2 zeta omega ns plus omega n square equal to 0. Poles. Okay, denominator equal to 0. So that's your denominator. So then make your denominator of this. So 1 plus g of s is 100 by s into s plus 4 into h of s, that is equal to 1 equal to 0. Then you will end up with s into s plus 4 plus 100 equal to what? 0. Then expanded. It is a square plus 4s plus 100 equal to 0. Compare this with second order. Now you will decide what is your damping. Tell me what is omega n square there. If given this way, that's how we need to proceed. So comparing these two, yes, omega n square equal to 100. Omega n equal to 10 radian per second. If that is the case, what is 2 zeta omega n? 2 zeta omega n equal to 4. What is zeta? Zeta equal to 4 by 2 omega n. Then what do you get? 4 by 20, right? Then automatically you'll get zeta equal to 0.2. Getting? Yes or no? Following, right?
Fine, sir.
Okay, yes, that's how. Suppose if given, and what is the damping of the given system, then that's how find the transfer function. Instead of transfer function, simply you can find the denominator equal to 0 and compare this with the a square plus 2 zeta omega ns plus omega n square. Or if you find the whole transfer function, you will end up with C of s by R of s. This is your R of s and this is your C of s. You will end up with 100 by what? A square plus 4s plus 100. Such a system is having static sensitivity of, in this case I can use k because system is not using. Okay, so here k is equal to 100, so let me say k1. Static sensitivity k1 equal to 1, omega n equal to 10, zeta is equal to 0.2. Like that you can understand what system is given to us. Okay, it's under damp second order with a damping of 0.2. So how the system is performing when excited by a step input, we'll see in the next session. Okay, so we'll apply a step input. We'll see how it is going to produce all the performances. So where we're going to talk about, so we're going to make our response C of t something like this, under damped second order system step response in detail. In this case, it's not AK, it is settling to A only. Response begins with 0 at time t equal to 0 seconds. Then it is going to have converging oscillations. Then the response will be something like this. Okay, getting everyone? Following right? That's your
Sir.
response. And a damp system producing the fastest response. 1 minute. Okay, like this. Roughly, I'm giving you the sketch. So this is the time I'm introducing the performance specs. How quickly the response very first time raises to the final value. This is a final value which is going to touch the final value after, already we know the settling time, that is 5 by zeta omega n seconds settling time. So very first time it is going to touch the final value, we're going to call it as rise time. That's first performance spec. We call it as rise time of the response. And second performance spec, at what time the response is reaching the maximum, We call it as peak time, that is denoted by TP. At this peak time, what maximum peak it is producing, we call it as maximum peak, denoted by MP. These are the performance specs of step response of a standard second order underdamped system. Performance specs. Rise time, peak time, maximum peak, and how much is your over peak with respect to the final value. So this is the net change in the output with respect to the steady state. With respect to the overall change, how much is your overshoot? This is called MPO. Okay, so this is your MPO, and this MPO is calibrated with respect to or measured with respect to the change in output. So this is your MP minus your final value, that is known as maximum peak overshoot. And this is defined in terms of percentage. How much is your maximum peak overshoot in terms of the percentage, that is read as maximum percentage overshoot, that is given by your MPO against actual change in output in terms of percentage, 100%. That is called percentage overshoot. And then we're going to find out few more parameters, like at what time the response settle within 5% tolerance band, at what time the system response settle within 2% tolerance band, at what time it is exactly settling without any tolerance. That is already known. So you'll be drawing tolerance band of, for example, 5% around your final value, 5% around your final value, that is 1.05 times A, up and down, 5% down, that is 0.95 A. That's a 5% tolerance band. So what is the time taken for the response to settle? The oscillations has to settle within this tolerance band. 5% up and below, okay, above and below your final value. So 5% means 0.05 A, therefore 1.05 A plus or minus 5%. So plus 5% 1.05 A minus 5% 0.95 A. So what is the time taken by the response to settle? The response to settle within 5% tolerance band means the response should enter the 5% band and it has to settle within that band. So first time it is entering, but here it is leaving. Second time it is entering, again leaving. Third time it is entering, again leaving. Again it is entering, again it is leaving. Here it is entering, after that it is not leaving. That's exactly the time needed for the response to settle within 5% tolerance band. Are you getting? Are you getting? Are you getting the point?
Yes, sir.
And similarly, we need to go for 2% tolerance band. And what is the time taken for the system, by the system response to settle within 5% tolerance band? So response should stay within that. Response should converge into 5%. That's what it means. Response should converge within 5% band. That's a time index known as TS 5%. Similarly, you can plot for two lines for 2% tolerance band. Then we can find out TS 2% and then TS 0% already known, approximately settling with no tolerance. That's a point. Okay. So all this performance specs we are going to calculate, we are going to deduce in the next session. Okay. So based on this only, a performance of a second order underdamped system will be defined. Okay, there are problems based on many parameters of this performance specs. Okay, so we'll be deducing them in the next session. We'll be first deducing raise time, followed by peak time, then maximum peak at this point and maximum peak overshoot at the same point, and then the percentage overshoot experienced by this underdamped system. Okay, and then settling times for 5% band and 2% band. We'll also find out one more performance spec, that is called decaying ratio, how quickly the response decays and settles to the final value, that is shortly denoted by DR, decay ratio. So these are all the specs deducing and these are all the specs determining how good your second order response is. If you're not happy with this, then we'll try to bring the controllers into the picture. So we'll bring proportional plus integral, we'll bring proportional plus derivative, and then proportional plus integral plus derivative controllers to improve the performance of the system. We'll see how we are going to improve them. Understood? Is it clear? So with this, let me conclude this session. Okay, we'll begin the next session by 3. Okay, so hope you're touching. Yes, exact. Okay. Any doubts we can discuss and then close the session. Anyone having doubts? Any comments on the speed? Are we going in reasonable speed? Or shall I decrease the speed or increase the speed? Yes, Varna?
So this is okay, sir.
Okay. Akshaya? Bharani Kumar?
Oh, sir. No problem.
Fine? Everyone comfortable with the speed? Yes?
Yes, sir. No.
Okay. Okay. Fine then. Fine then. Okay.